Welcome students to our video notes lesson on section 5.1, which is on slope fields and differential equations. We learned a little bit about differential equations at the very beginning of 4.1, and we're going to revisit those here in chapter 5 and even do some more complicated ones. Before we get into all that stuff though, I want to start by getting a visual sense of what a slope field is and how they relate to differential equations. So we're going to start by creating a slope field, or what is also sometimes referred to as a direction field, for a very simple differential equation. dy dx equals x. So really quick side note, what is a differential equation? It's basically an equation that contains both variables, like it could have an x or a y in it. In this case, this one's got an x. But this equation could also contain derivatives, like dy dx, or sometimes this is referred to as y prime. This one's got the dy dx. So this is a differential equation because it has a derivative in it along with x. And really this is just telling me that the derivative of y with respect to x equals x. So it's an equation telling us what a derivative of y is. And so the solution to it would be whatever y equals, whatever the antiderivative is. And the slope field is a way for us to kind of help visualize the solution to this differential equation. And let's see how. So the way we make a slope field is we kind of just start by a table of values. So because this derivative is only in terms of x, I would just need one column for my x inputs, and then I would calculate whatever dy dx is based off of x. Now in this case, dy dx just equals x, so this is a very simple one that we're starting with. And I'm just going to use all my x's from -5 to 5 in this particular grid. So I'll just plug in all those x's here. And then my derivatives, my dy dx, according to this equation, just equal x. So these will be all of the same values. Now, what we are going to draw here are little mini tangent lines, because what a derivative is, what a dy dx is, it's a slope of the tangent line to y, right? The dy dx is the slope of the line tangent to y at these given x's here. So for example, when x is -5, the slope of the line tangent to y is equal to -5, and so on and so forth. So over here where x is -5, I'm going to draw tangent lines that have slopes of -5, but I'm not going to be like super accurate about it. It's going to be more like relative. So -5 is the steepest of the negative slopes in this set of slopes, and it's negative, so it's facing down. So I would just draw a bunch of steep lines that are facing down. And I'm going to go all along all these different y values. So we're going to make a field of slopes, right? A slope field. So when x is -5, all of my tangent lines at all of these different y values would be -5. Then I'm going to come over to -4 and make it slightly less steep. So again, I'm not actually counting, down 4/1. It's more relative, right? This line will be still facing down and a little bit less steep than -5 was, and then so on and so forth. And -3 would be slightly less steep, and so on and so forth. Now when you get to the 0, remember a line that has a slope of 0 is horizontal. So these would be horizontal tangents. So we would draw them like this. Now we move over to the positive. So when x is +1, my tangent line also has a slope that's +1. So now my lines will be facing up, and they won't be very steep because it's just a slope of 1. But the bigger x gets, the more steep my tangent lines get because their slopes get bigger. So I just kind of, for 2, I draw a line that's like slightly steeper than 1. And then 3 would be slightly steeper than 2. And 4 steeper than 3. And then 5 would be my steepest in this set of slopes. Okay, so what we've created here is a field, a direction field, showing me all the different possible tangent lines to all the different possible solutions to this derivative or this differential equation. And so that's what a slope field is basically. So I'd like you to write this down on your outline. It's a graph with tiny line segments, as you can see here. And what they are denoting are all the possible tangent lines to the function that would be the solution or the antiderivative to this differential equation. So I want you to take a look at this solution field and ask yourself, what shape do these mini tangent lines seem to be forming? What does it look like to you? So I'm hoping you're kind of envisioning a parabola, right? Where these look like they could be graphs of parabolas, all different kind of parabolas, right? And so a possible equation for that, for y, could be x squared. And this is because this is our sort of parent equation for any graph that looks like a parabola. Of course, this is the one centered at the origin, right, and facing up. So that's just kind of like a guess at what the solution to this differential equation right here could be. So now we're going to go ahead and find the actual solution. So this is our guess right here. We're going to use these steps here to solve and find what that true antiderivative is. Of course, many of you are probably already know what it is, but anyway, let's just use this simpler example to kind of go through these steps. Now, what we're finding when we're finding a general solution is the antiderivative plus c, right? The plus c kind of takes care of every single possible solution to this differential equation. We kind of think of it as like a family of functions. So in the general solution, we don't solve for c. We just get an equation with the plus c at the end. Now, when we are solving a differential equation, what we should always begin with first is what we call separating the variables. Now, in this particular differential equation, it's only in terms of x, so you wouldn't necessarily need to separate the variables for this one, but I want to show you all of the steps that we would need to go through for every type of differential equation, which is why I'm taking the time to do step one. Because when your derivatives eventually are going to be in terms of both x and y, you will need to separate the variables first. What we mean by that is you take the dx and you bring it to the other side, multiply it to the other side. So we start with this. dy is equal to x dx. These two statements are saying the same thing. And then what we do is we integrate both sides, and then we add c. So when I'm integrating 1 with respect to y, the value for that is just y. And when I'm integrating x to the first power with respect to x, I would use the power rule here and get x squared divided by 2, and then plus c. So it's important that you add c on the same step where you integrated. And then we plug in an initial condition if provided, but I wasn't given one here because I'm just finding a general solution. We only do this if we're solving for c. And then we solve for y. So in this case, y is already alone. This basically just means isolate y. But I don't need to do that here because it was already isolated. So this is my solution. And many of you probably already realize that, because if I take the derivative of this, right, derivative of y with respect to x, I would do 2 times x to the first over 2. Derivative of a constant is 0, and this would just be x, right? So this here is my solution to the differential equation because its derivative equals x. So that's why if you look at your slope field up here, we have some parabolas that are way up at the top, some that are kind of in the middle, and some that are at the bottom. Because this plus c right here is being added to my parent function for a parabola, my x squared function. So basically the plus c just sort of shifts the graph up or down. It shifts our antiderivative up or down. And that's how I end up with an entire field of slopes. And that's just taking into account parabolas that have been shifted up or down. Okay, so then sometimes what we're asked to do is find a particular solution. And in this case, it wants us to find the one that goes through this point right here, -3, 2. So we're going to go back to our slope field and trace that curve to see what particular graph that would be. So we're going to come back to our slope field. We're going to find the point -3, 2. And we're going to go ahead and sketch in the slope field. So what we want to do is sort of follow the slopes. So we don't want to like cross the slopes. We want to sort of follow them and be sort of tangent to them. Like this. And like that. So we don't want to cross or be perpendicular to any slope. We always want to be tangent to the slope and just sort of follow the direction. Sorry, this looks really messy. But anyways, you get the idea. So it's this parabola right here that's sort of crossing the y-axis somewhere in the negative area. So this is the particular solution to this differential equation that passes through the point -3, 2. That's what this graph in pink is. And I can find it on my slope field. And now what I'm going to do is solve for it by doing step 3 above, right? Step 3, plugging in the initial condition, is what we do when we're asked to find a particular solution, which does not have a plus c, right? It's a specific antiderivative for the differential equation that passes through a particular point, and therefore we solve for c. So I'm going to take it from where we left off. So we left off at y equals x squared over 2 plus c, and I'm going to go ahead and plug in these ordered pairs. So I'm going to plug in 2 for y and -3 for x, and then solve for c. Okay, so I found out that my constant is -2.5, so my particular solution would be the x squared over 2 minus 2.5 equation. All right, so in example 2, we're going to do the same series of steps we did before, but now we're looking at the differential equation where we have the derivative of y is equal to 5 over x. So again, just like the last time, I'm going to go ahead and make a table of values. And since my grid here is going from -5 to 5, I think I will do the same thing for my x's. And then for my slopes, which are my derivatives, right? This is a slope of a tangent line. It'll be 5 divided by whatever the x coordinate is. So that would be -1 here, -1.25. This would be -5/3 or -1 2/3. This would be -2.5, -5. And then this would be 5 over 0, which we understand is undefined, but we can also understand that as a vertical tangent. So when we draw that tangent line, we would just draw a vertical tangent, and that's the type of tangent line that doesn't have a slope because its slope is undefined. And then this would be 5, and then 2.5, and then 1 2/3, and then 1.25, and then 1. Okay, so just like with the last one, when I'm sketching these slopes, I'm just sort of sketching them relative to each other. So my steepest slope, maybe I'll just highlight that. My steepest slopes will be at -1 and 1. And then everything else just kind of gets less steep from there. So I know that right here when I'm at -1, I have these like super steep slopes of -5. And then when I'm at +1, I have the super steep slopes going up of +5. And then along 0 is where I have my vertical tangents. So it's basically what it is a vertical asymptote. And then from there, they sort of get less steep. So then when I go to -2, it's half as steep as it was when it was at -1, because now I'm going from -5 to -half of 5. And when I get to -3, it's about -1 2/3. So it'd be really similar in steepness to what it was at -2, but just a little less steep, but similar. So on and so forth. Okay, so now that we have our slope field, we can maybe try to make a guess at what the equation for this one's going to be. It's not as obvious as the one before, but it does look like it's something that would kind of make this a shape that kind of looks like this, or on the other side kind of looks like that. So I don't know if that kind of rings a bell, what function that might be, but let's go ahead and find the general solution to get the equation for the curve that would have this type of direction. So we start by separating the variables. So we're going to take the dx and multiply it over here. Then we continue with integrating both sides. And again, when I integrate 1 with respect to y, I just get y. And then for this side, we could think of that as 5 times the integral of 1 over x dx. So I'm hoping that you remember what the antiderivative of 1 over x is. And if you're thinking ln of x, you would be correct. And then, of course, we put our x in absolute value when we're integrating, plus c. So this is our general solution for the differential equation above. And so I was hoping that maybe you were thinking of the natural log because that's the graph that kind of goes like this, right? It has a vertical asymptote at 0. And because we have x in absolute value, we could also have a different one on the left where x's were negative. But now I can plug them into the natural log because I'm taking the absolute value of x. So it's either one of these sides. Okay, so now what we're going to do is find the particular solution that passes through the point 2, 2. So let me get rid of these solutions here. So 2, 2 would be right here. So we're going to trace our solution. So it would be this one here. So that would be our particular solution that passes through the point 2, 2 and has this derivative, 5 over x. So we're going to take it from where we left off in part B. We're just going to use the 2 over 2 to solve for c. So I'll plug 2 in for y and then 2 in for x. And so I know that 5 times ln of 2 is the same thing as ln of 2 to the 5th power, which is ln of 32. So then I would subtract that from 2. So that's what my c equals. My c equals 2 minus the natural log of 32. So then my particular solution, the one that is one specific graph, would equal 5 times the natural log of the absolute value of x plus 2 minus the natural log of 32. I did not need absolute value here because I know that 2 is already positive. So you don't need to also put absolute value around it because it's already positive. So this would be our particular solution to example 2. So now I'd like you guys to go ahead and try one. I want you to make your slope field, come up with a general solution for both A and B. Okay, so here are the slope field values I got for the first U-try. I only went to -3 because the slopes were already getting so steep that I figured there's really no point in finding what they actually are at -4 and -5 because they're just going to be so steep, they're just going to kind of almost look like straight lines, like vertical lines. And I basically can see the trend that they get as you move to the left, as x moves to the left, the slopes get steeper, and then same thing, as x moves to the right, the slopes get steeper gradually. So you just make each slope on the right steeper than the one on the left to the point where it almost looks vertical over here, where x is 5, because it would be a slope of 75. Anyway, so this is, kind of an idea of what the slope field would look like. Now, it's okay if answers vary slightly because it's all how we interpret these slopes to look, but they basically would all be positive slopes, and they're all fairly steep, and then you'd have horizontal lines in the middle. And so you may have recognized that 3x squared is just the derivative of x cubed, so these are just all the graphs of cube equations, x cubed equations. The parent one sort of goes through the origin, but because we're adding c here, it could be a cube function that shifted up a little bit, or it could be one down here that shifted down a little bit. So these are just all of the different cube root graphs centered at 0, 0 with maybe some sort of horizontal shift based on whatever the constant might be. So that was A. And then B, of course, was a little bit trickier. So for this one, we're going to have to use special angles off of the unit circle, these ones here. I used ones that are easy to evaluate tangent of, and also ones that I kind of know where they would fall on the x-axis. I know pi would be somewhere just a little bit more than 3. Pi over 2 would be a little bit more than 1.5. It's like 1.57. Pi over 4 would be about half of that, and so I just kind of pictured it that way. So I put my pi here, and then pi over 2 there, and then I just put halfway marks for the pi over 4s. And what you do when you're evaluating tan squared x, it's the same thing as finding tan of x and then squaring it. So at pi, tangent is 0 and 0 squared is 0. At pi over 2, or negative pi over 2, tangent is undefined, because technically it would be -1 over 0, which is undefined, so you do vertical lines there. So all the pi over 2s have vertical tangents. And then so on and so forth. These were the values that I found. So this is the slope field it kind of generated. Looks kind of strange. But we had a lot of like 0 slopes, and then slopes of 1, and then vertical slopes, and then slopes of 1 again. And all the slopes were positive, right? Because I'm squaring this tangent, so my derivative values are always positive. So then when you go to solve this differential equation to get the general solution, which is right here, we have to use a trig identity because we do not have a formula that tells me the antiderivative of tangent squared. But what we do know based on our trig identities is that if I do tan squared x plus 1, that's equivalent to or the same thing as secant squared. And then if I subtract 1 from both sides, that tells me that tangent squared x is the same thing as or equivalent to secant squared x minus 1. That means they can be used interchangeably. So I can swap out the tan squared x for the secant squared x minus 1. And I do know the antiderivative of secant squared is just tangent, because the derivative of tangent is secant squared. And the antiderivative of 1 with respect to x is just x, and then plus c. So you might be wondering what the graph of this looks like, because it's a little bit hard to tell from the slope field here. But basically it's a bunch of tangent graphs that gradually get higher and higher as you move to the right. So this one would be like up here, and then the next one would be a little bit higher. So tangent functions minus x, meaning that there's sort of a linearness to this as well, right? It still kind of has like a slope trending this way. Anyway, so that's kind of what the graph of that would look like. You could check it out on Desmos if you want, graph it there. But at any rate, this is our solution, tan x minus x plus c. Okay, so the last part of this video is learning how to make slope fields when our differential equation is in terms of both x and y. Now, we're not going to learn how to solve these until our next video for section 5.3. Here, we're just going to learn how to make the slope fields. So it's important for us to understand that if our derivative is in terms of both x and y, I need both an x and a y column as well as my derivative column, because I have to know what both x and y are to find my slopes. Also, that means that, like, for example, at x equals -1 and at y is 0, that'll give me one type of slope, -1, or no, +1 over 0, which is undefined. But at -1, 1, which would be right here, that would give me a slope of 1 over 1, which is 1. So the slopes are not going to be the same as you go up and down one particular x value. So these slope fields take longer to make, as you can imagine. Although one thing I'm noticing with this one is that anytime y is 0, I'm going to have vertical tangent lines. So y is 0 whenever I'm on the x-axis. So I know that all of these points will have vertical tangent lines. So that one kind of helps me eliminate having to make all of those slope fields. And then another thing I notice is that whenever y is 1, so if all these here would just equal the x value, right? So like if x is -2 and y is 1, then that would just be, be the opposite sign of x. So then I can say, well, if this is a slope of 1, I know that this would be a little bit steeper, a little bit steeper, a little bit steeper, a little bit steeper, right? Because this is 1 over 1, 2 over 1, 3 over 1, 4 over 1, 5 over 1. And then I know the same thing would be true over here, and this would just be 0, right? Because this would be x is 0, y is 1. And then on this side, when x is +1, then the slope would be -1. So then it would be like that, and then they would gradually get steeper as you move to the right. -2, -3, -4, -5. So it's just kind of all relative. Okay, and then when I go up to where y is 2, for example, and another thing I'm noticing, I'm noticing that if x is 0, for all the places where x is 0, my slope would be 0 over y, which is 0, which is a horizontal tangent line. So I know that all along the y-axis, which are the values when x is 0, I have, and then this one just doesn't have anything, because 0 over 0, right, when x and y are 0, is indeterminate. That's different than undefined. That's just like, we don't know what that is, so there's just nothing there. And then these would all be horizontal. So there are kind of some patterns we can notice to help us not have to plug in every single one of these points. But notice that I will have to plug in quite a few more values to kind of see what that trend is. So maybe I'll do a couple down here when x is -1. That's this one. And then y is 1. My slope would be negative 1 over 1, right? Negative x over y, which is 1. Oh, sorry, y was negative 1 here. There we go. So these slopes will be the same value as whatever x is. For example, when x is negative 2 and y is negative 1, I would have negative 2 over negative 1, right? Negative x over y, which would be 2 over negative 1, which is negative 2. So for all of these values where the y is negative 1, then the slope is just equal to whatever x is. So then this would be a slope of negative 1, and then negative 2, negative 3, negative 4, negative 5. And then keep going. So sometimes for these, we have to make a couple different tables to get enough values to kind of picture what our slope field would be. So let's do this, let's do these points over here, where x is 1 and y is negative 1. Then my derivative, which equals negative x over y, would be negative 1 over negative 1, which is 1. If x is 2 and y is negative 1, then my derivative would be negative 2 over negative 1, which is 2. So it's the same thing. For these points, my slope value equals whatever x equaled. So this would be positive 1, positive 2, 3, 4, and 5. So let's do one more row. Let's do the one here where y is positive 2 and then where y is negative 2. Maybe we'll start with this one. So that would be where x is negative 1 and y is positive 2. So my derivative, which is negative x over y, would be 1/2. And then when x is negative 2 and y is 2, then it would be 2/2 or 1. And then so on and so forth. So I do notice that the slopes are increasing, right? They went from 1/2 to 1 to 1.5. So they're getting steeper, but they're not as steep as the row below. So this would be a slope of 1/2, which would maybe be like that. And then this would be 1. So like this slope should match that one. And then a little steeper, a little steeper, a little steeper. And just from noticing a pattern, my guess is it's kind of the same thing over here on the right. And then let's do the row down here where y is negative 2. So I'll start with this point, and maybe this one too. So I'll do when x is negative 1 and y is negative 2. So my derivative would be negative x over y, so 1 over negative 2. And then when x is negative 2 and y is negative 2, or no, sorry, let's do when x is 1. X is 1, that's right here, and y is negative 2, then I'd have negative 1 over negative 2. So I'm thinking it's going to be the same. This row here will be the same as this one, and then this row down here will be the same as the one up there. So then this will be negative 1/2, negative 1/2, negative 1, negative 1.5, steeper and steeper, and then positive 1/2, positive 1, positive 1.5, steeper and steeper. And it just will continue building. So you can see these take a lot longer to make. And so usually the textbook will give you a smaller range to work with, or it'll say find it at these particular 9 points or something like that. But I wanted you to kind of get a good visual of this one, which is why I thought we would do a few more and kind of recognize some patterns, because I want you to make a guess at what you think the general solution to this differential equation, the one up here, might be. So I hope you're noticing that this kind of looks like these are forming circles, right? Hopefully you're kind of noticing that, and they get larger as you move further away from the center. So a general equation for a circle would be something like this. X squared plus y squared equals r squared. And this r squared right here is just a constant, right? It's just whatever the radius of the circle is. So that could be our c value. Or if we were putting this in terms of y, we could think of that as plus or minus the square root of c, which is r squared, minus x squared. So that's coming. Next section, we're going to show you how you could get here from this differential equation right here. But you can see on the slope field that it is forming the shape or the graph of circles. Now what I want you to do, I already kind of drew on it, but on your slope field, I want you to find the point negative 3, 0, and let's make a guess at what that equation would be. So let's do that. Sorry, negative 3, 0, that was right here. So that would be, if I followed these slopes, that would kind of be going like this. So it looks like, sort of, right, if I'm following the slopes. So it looks like if I'm passing through the point negative 3, 0, that this would be a circle with a radius of 3, right? It's going 3 on the right, 3 up, 3 on the left, 3 down. So I would guess that this may be the equation x squared plus y squared equals 9, right? Circle with a radius of 3. Or perhaps if I was solving for y, it would be y equals plus or minus the square root of 9 minus x squared. We have to put both the positive and the negative because it has both the top and the bottom half of the circle. Okay, so that's technically how you would do a slope field for a differential equation with x and y. So I'd like you to try a couple of these as well. This one's not too bad because it's only in terms of y. This will be a little easier. But this one here, you will have to do a number of points. So see if you can find some patterns that help you kind of just plug in a few points and then carry the pattern out. So pause your video, try it, and then check. All right, let's check out your slope fields and see how you did. So this one here, where the derivative was only in terms of y, wasn't too bad. All we had to do were plug in y values, which are going along the y-axis. And I noticed that on the negative side, the slope started off pretty gradual, and then they kind of slowly got steeper as you went towards 0, and they were facing down. So that was down here. So these were the negative 1/5, negative 1/4, negative 1/3. So they're getting less and less steep, all facing down. And then the opposite on the positive side, starting at 1, they were very steep and then got less and less steep as the y value got higher. So you can see them kind of flattening out. So your slope field should look something like this. Of course, everyone's slopes are a little relative as long as you get the same general idea of the solution. So I wonder if you guys could make a guess at this. What do you think this might be a graph of? Make a guess. Let me know when I see you in class. We're going to learn how to solve these coming up soon, so that's exciting. Now this one, I got tired after I got to this row here, so I only did from y going from negative 2 to 2. But I did notice some patterns. I noticed that whenever y was 0, I would have a slope of 0, so that was all along the x-axis. And I noticed that whenever x was negative 1, I had another slope of 0. So that was along here. And then I noticed some patterns with these rows. They kind of got steeper as you went to the right and the left. So this one kind of looks like, I don't have the top filled out, but it almost looks to me like it's got a parabola opening up and then another one maybe down here. Anyone remember what that's called? I don't even know if they teach those anymore. What is that called? And how the heck does that become its derivative? That is the question of the day, and I cannot wait to get into that with you guys. That's coming up. Now, for our last example, we're just matching, right? We're just matching which one of these belongs to which of these differential equations. So one thing I tell students off the bat is look to see if your derivative is in terms of only one of the variables or whether it's in terms of both. So I noticed that b is only in terms of y. That means the slopes are going to be the same as you go along the x values because the slopes don't change based on x. And I notice right here that when y is 2, I have a slope of 0. Now that would match this derivative, right? Because if I did 2 minus 2, I would have a 0. So that's why I'm thinking that this graph right here matches my differential equation in part B. Because the slopes only change as I go up. They don't change as I go across. And because they're 0 when y is 2. Then for C, I would kind of look for something similar. I would look for a graph where the slopes don't change when x changes. So this is the other one when the slopes are staying the same for each x value, but they're changing as you change the y value. And if I maybe pick a slope like right here, that looks like the point 0, 1, the slope for that would be 1/2, which this does look like a slope of 1/2. And so on and so forth. So I'm thinking that this graph matches differential equation in part C. D, I'm going to D because this has everything in terms of x. So that means the slopes would be the same as you go up and down, right? They don't change as y changes. They only change as x changes. Also, I know that the antiderivative of this would be x squared over 2. So that would look like a parabola, which is what this looks like. So this one I know matches the differential equation in D. which of course, process of elimination, I know this is A. But what you could look for is the fact that the slopes change as I change x and y. The slopes change as I go left to right and up to down. So I know that it's changing based on both x and y, which is an indication to me that it matches differential equation in part A. All right, so I will see you guys in class where we will be making slope fields, matching slope fields, and all of that good stuff. Can't wait. See you there.